Two pieces of metal pushed into wet dirt. That is it. No fuel, no solar panel, no generator, no moving parts. Nothing to plug in, nothing to charge beforehand. Just two different metals buried a few inches into moist ground, connected by a wire producing real measurable electricity. A Scottish inventor used this exact principle in 1841 to power a telegraph system across miles of open countryside, and it ran for months without a single maintenance visit. The United States government itself used this technology to power sections of the early National Telegraph Network in 1848, and filed official reports with the Smithsonian documenting exactly how it worked. That was 175 years ago. So why have you never heard of it? Why is there not a single product based on this principle in any camping store, any survival kit, or any emergency preparedness catalog in the country today? The answer to that question is going to change how you think about every battery you have ever bought. Stay right here. Welcome to Everyday Secrets Formula. This is where we dig into the knowledge that has been quietly removed from the mainstream conversation, trace it back to its origins, explain the science clearly, and follow the money to understand why something this useful never made it onto a store shelf. If you're new here, I'm glad you found this video, and I genuinely think you will want to stay for the ones that come after it too. Hit subscribe before this video ends. Now let us talk about the ground beneath your feet and what it has been capable of producing your entire life without anyone telling you. Before we get into the history, I want you to picture something for a moment. You are 3 days into a backcountry camping trip. Your phone is at 2% battery. Your headlamp batteries died last night. You have no solar panel because the tree canopy has been blocking the sun since you set up camp. And you have no way to recharge anything because there is no outlet within 40 miles. Now picture reaching into your pack, pulling out $5 worth of hardware store materials, pushing them into the ground around your campsite, and having a functioning power source within 20 minutes that charges your phone, runs your LED lantern all night, and keeps going without any fuel at all. That is not a fantasy. That is a documented, scientifically confirmed, historically proven capability that has been available to every person on Earth since before electricity was even a formal field of study. And the reason it feels like a fantasy is not because it does not work. It is because an industry generating $150 billion a year in battery sales needs you to keep believing that electricity requires expensive, replaceable, proprietary technology that only they can provide. Let us start at the beginning, because the history here is genuinely extraordinary. The year is 1841. A Scottish clockmaker named Alexander Bain is working in a modest workshop in Edinburgh with no access to academic institutions, no wealthy backers, and no formal scientific training. What he has is relentless curiosity and a willingness to experiment with things that most people of his era would not take seriously. One afternoon, he drives two different metal rods into the damp soil behind his workshop. One is copper, one is zinc. He connects a wire between them and attaches a measuring device. The needle does not just flicker, it holds steady. A continuous, sustained current flowing from nothing but two metals and the earth between them. Bain files a patent that same year, patent number 963, formally registering what he calls the Earth battery. He uses it to power his electric clock designs and then scales the concept up significantly. By 1843, he demonstrates that Earth batteries can drive telegraph lines across open distances without any conventional power source involved at all. Think about what that meant in 1843. The telegraph was the most important communication technology of the era, the equivalent of the internet in terms of its social and economic impact, and Bain had just shown that it could run on dirt. But Bain was not working alone in history. 50 years later, in 1892, a farmer in Murray, Kentucky named Nathan Stubblefield took the Earth battery concept even further. Stubblefield buried metal coils in the ground around his farm, connected them to a device he built himself, and on a cold January morning invited a group of witnesses to his property. He picked up a receiver, and they heard his voice transmitted wirelessly across the farm. No connecting wires between transmitter and receiver. No conventional power source of any kind. Just Earth batteries driving the entire system. The local newspaper described it as something close to a miracle. Stubblefield demonstrated the same technology in Washington, D.C. in 1902, transmitting voice across open water on the Potomac River in front of a public audience. Multiple successful demonstrations, documented results, and then nothing. No major company invested in his work. He died alone in 1928 in a shack on his own property, with his devices scattered and his patents expired without commercialization. He is almost completely unknown today, despite the fact that his work predates much of what we credit to more famous inventors. Now go back even further than Stubblefield or Bain, because this is the part that puts everything in perspective. In 1938, archaeologists working near Baghdad discovered a clay jar roughly 5 inches tall. Inside the jar was a copper cylinder with an iron rod suspended at its center. The artifact dated to approximately 250 BC. When researchers at General Electric later filled a replica of the jar with grape juice as an electrolyte, it produced between 1.5 and 2 volts of electricity. This object, now known as the Baghdad battery, predates Alessandro Volta's famous electric pile by over 2,000 years. Someone in ancient Mesopotamia, before the Roman Empire existed, before the birth of Christianity, figured out that two different metals separated by an acidic liquid produce an electric current. This is not a fringe interpretation. It is a measured, replicated, laboratory-confirmed result. The principle that produces voltage in that 2,000-year-old clay jar is the exact same principle that will power your phone charger in the ground of your next campsite. The chemistry has not changed in 25 centuries. What has changed is who profits from controlling your access to it. The science behind all of this is called galvanic reaction, and it is one of the most thoroughly documented principles in the entire field of electrochemistry. When two metals with different positions on the electrochemical series are placed in an electrolyte, meaning any liquid or substance capable of conducting ions, electrons flow spontaneously from the more reactive metal toward the less reactive one. That electron flow is electrical current. It is not complicated. It is not experimental. It is a law of physics that every first-year chemistry student learns, and it has been confirmed across thousands of studies over more than 2 centuries of scientific research. The reason soil works as the electrolyte is that it is already a natural ionic conductor. It contains water, dissolved mineral salts, or organic acids produced by decomposing plant matter, and billions of microorganisms whose metabolic activity further enhances its conductivity. Every handful of forest floor soil is already a chemical environment perfectly suited to drive this reaction continuously and indefinitely as long as it stays moist. The voltage a given pair of metals produces depends on how far apart they sit on the electrochemical series. Zinc and copper together produce approximately 1.1 volts per cell. Magnesium and copper push closer to 2 volts per cell. Aluminum and copper fall at around 1.5. A single cell is modest, but this is where the design thinking becomes powerful. Connect 10 zinc and copper cells in series and you have roughly 11 volts. Connect 15 cells and you're past 12 volts, which is the standard threshold for USB charging. The University of Wisconsin published research in 2017 measuring sustained current from soil-based galvanic cells over a 90-day period. The cells showed less than 12% degradation across 3 months of continuous operation. For context, a conventional alkaline battery sitting unused on a shelf loses up to 20% of its stored charge through self-discharge in the same period. The Earth battery, by comparison, is not storing energy that slowly leaks away. It is generating energy continuously from an ongoing chemical reaction in the ground around it. The United States Department of Agriculture has published soil conductivity surveys showing that most forest soils in North America fall well within the electrical conductivity range needed for effective galvanic output. In practical terms, the dirt under almost any campsite in this country is already a functioning electrolyte waiting for 2 pieces of metal. A team at MIT demonstrated in 2015 that microbial fuel cells, operating on a nearly identical principle, could power remote agricultural sensors continuously for over a year with 0 maintenance required. These are not theoretical numbers from controlled lab environments. They are field-tested, peer-reviewed, and repeatedly confirmed results from some of the most respected research institutions in the country. So why, with all of that documented evidence and all of that history, is there not a single Earth battery product in any outdoor retailer in America? Why does a technology that the United States government formally documented and used in 1848 not appear in a single modern survival guide, emergency preparedness manual, or camping equipment catalog published in the last 50 years? The answer is the same answer that explains the absence of so many genuinely effective, low-cost, self-sufficient technologies from the consumer marketplace. Follow the money. The global battery industry generates over $150 billion in annual revenue. The average American household spends more than $150 every year on disposable batteries alone. Multiply that across 130 million households, and you begin to see the architecture of what is at stake. The entire business model of the portable power industry rests on a single operating assumption. You believe that electricity requires complex, proprietary, replaceable technology that you must purchase repeatedly from manufacturers who control the supply chain. Remove that assumption, and the industry loses its customers. Now consider what the Earth battery represents from that industry's perspective. The raw materials cost under $5. The electrolyte is literally the ground underneath your feet, which covers the entire surface of the planet and cannot be owned, patented, or metered. The reaction renews itself continuously as long as the soil stays moist, which means there is no expiration date and nothing to replace on a regular schedule. You cannot patent the electrochemical series because it is a law of nature. You cannot build a subscription model around copper and zinc because any hardware store sells both metals by the pound for a few dollars. You cannot justify a $200 portable power station when a child can build a functioning electricity source in a backyard using a handful of pennies and some galvanized nails. The Earth battery does not fit inside the revenue model of the portable power industry. It does not just compete with that model, it makes the model look unnecessary. And so it was not banned, because banning it would draw attention to it. It was not publicly debunked because the science is irrefutable, and any attempt to debunk it would only amplify awareness. It was simply allowed to fade, removed from textbooks gradually, left out of hardware store inventory entirely, absent from every mainstream survival and outdoor publication for the better part of a century. The same quiet disappearance that has happened to every self-sufficient technology that threatened a profitable dependency. In 2012, a researcher at Harvard University published a paper on microbial fuel cells that function on essentially the same principles as Earth batteries, demonstrating that these cells could produce enough power to run small electronic devices using nothing but soil microbes as the energy source. That paper was cited over 300 times in academic journals. It influenced research at universities and laboratories around the world, and not a single commercial consumer product emerged from it. 300 peer-reviewed citations and 0 products for sale. Because the profit margin on self-sufficiency is 0, and the companies that might productize this technology are the same companies whose existing revenue depends on you not having access to it. Now here is exactly how to build one yourself, and I want you to notice as I walk through this how genuinely simple it is. You need 2 materials from any hardware store: 14-gauge solid copper wire and standard galvanized steel nails. The galvanization on those nails is a zinc coating, and zinc is your second electrode. Copper is the first. These 2 metals, copper and zinc, give you the best combination of voltage output, availability at any hardware store, and low cost for practical field use. Cut the copper wire into strips approximately 6 inches long. Use standard 3-inch galvanized nails as your zinc electrodes. Find a patch of ground with moist, mineral-rich soil. Forest floors, garden beds, and areas near streams or water sources are ideal. Avoid dry, sandy, or heavily compacted soils, as these have lower ionic conductivity and will reduce your output. Push 1 copper strip and 1 galvanized nail into the soil, approximately 4 inches apart from each other, burying each one at least 3 inches deep. That is your first cell, and depending on your soil conditions, it will produce between 0.8 and 1.1 volts. Now here is the critical step that turns a science experiment into a functional power source. Connect your cells in series. Run a wire from the copper strip of cell 1 to the zinc nail of cell 2, then from the copper of cell 2 to the zinc of cell 3. Continue this pattern across as many cells as you need. Each cell adds its voltage to the running total. 10 cells give you roughly 8 to 11 volts. 15 cells push you past 12 volts. Add a simple voltage regulator, which you can purchase for under $2 at any electronic supplier or online, and you have a stable, regulated power output suitable for USB device charging. The complete setup for a 20-cell array takes approximately 20 minutes to assemble in the field. Total material cost for the entire system is under $5. A camper in northern Maine documented his results with a 20-cell copper and zinc earth battery during a week-long backcountry trip. He reported charging his phone 3 times across the week and running an LED lantern every night from dusk until he fell asleep. His total material investment was $4.37. I want to be straightforward with you about what this technology does and does not do, because accuracy matters more than hype when it comes to something you might actually rely on in the field. Earth batteries produce low current. They are not going to run a refrigerator, power a space heater, or supply a full cabin. They are best suited for low-draw applications, charging phones and small devices, running LED lighting, powering emergency communication radios. I want to hear from you on this one. Drop a comment below and tell me whether you're planning to try this on your next camping trip, or whether you want to test it in your backyard first, just to see the electricity flowing from the ground before you trust it in the field. Either way, share your plan and let the community know what you are thinking. And if you have a friend who has ever been stuck in the backcountry with dead batteries and no way to recharge, send them this video, not as a general suggestion, specifically, because the information in it is worth more than every battery they have ever thrown away. Subscribe to Everyday Secrets Formula so you are here when the next one comes out. Every video on this channel follows the same thread: real solutions that were quietly replaced by profitable dependencies. And we are nowhere near done pulling that thread.